Now we're going to look at properties of conservative vector fields. In order to do that, we're going to need to know a few things about curves and regions in space, particularly the kinds of curves and regions we'll be interested in. So a curve is called simple if it doesn't intersect itself. So here's a couple of curves drawn that are simple, whereas the ones on the right, these are not simple curves. They're self-intersections. A curve is called closed if its initial point corresponds with its terminal point. So there's a couple of curves that are closed. The other ones, the two in the top row, aren't closed. Their terminal and initial points don't coincide with each other. So this one in the bottom left is an example of a simple closed curve. In terms of regions, a region is called open if for every point in the region there is a disk centered at P that's small enough so it lies entirely inside D. And if we have a region that's open, typically we would use a dotted boundary because those are really the places that are going to determine whether our region is open or not. So for example, if I look at a point, say right on the boundary, then any disk, no matter how small I draw around that point, is always going to contain points outside the region and points inside the region. So if I'm interested in an open region, then we would typically draw these regions with dotted boundaries to indicate those boundary points aren't in the region itself. So we would use these dotted boundary curves to indicate that it's open. A region is called connected if for any 2 points in that region they can be connected by a path that lies entirely inside the region. So it means if I've got a point and I connect it to another point, then that path is going to be entirely inside the region. Unlike this one in the bottom right where I can pick 2 points, maybe a point there and a point there, and no matter how I draw a path, it's going to have to leave the region. So that would be not connected. Now, in particular, we are interested in regions that are going to be simply connected. So that is connected regions that are a little bit more robust in how they're connected. So we say a region is simply connected if every simple closed curve in the region encloses only points that are in D. So if I think of a simple closed curve here, then that encloses only points in the region D. Whereas this one in the bottom left, I could find a curve that when I draw it, it's a simple closed curve, but it doesn't enclose only points in D. There's this sort of hole in the region D which doesn't have points in D, and that's interior to or in the inside of our curve. And so this region is not simply connected. We can sort of think of it as simply connected just means there's no holes in it. And this one on the right, it's not simply connected because to be simply connected, we first assume it's connected and then it's more robust than that. Any closed loop around it must contain only points in D. So there's none of these holes. So what we will be interested in is in simply connected domains, simply connected regions. That's where our focus will lie. So that's why we've given this introduction to these characterizations of curves and regions, is because we're going to be interested in the simply connected regions for classifying conservative vector fields. Okay, so here comes our classification of conservative vector fields. Let capital F be a vector field over an open, simply connected region D. The following are equivalent. F is conservative, so that means F is the gradient of some potential function. The integral along any curve for F is independent of the path from x0 to x1. So this is known as independence of path or path independence. Now I've put it in italices there because I've given the precise definition of what it means to be independent of path. It means that if F is continuous, a continuous vector field with domain D, we say that the line integral, the integral along C of F dr, is independent of path if the line integral along C1 is the same as the line integral along C2 for any two paths in D that have the same initial and terminal points. So it's independent of path if the line integrals only depend on the initial and terminal points. Now we've already seen from the fundamental theorem of line integrals that if f is conservative, then it's independent of path. So what we've already seen is that A implies B. So that if A is true, then we know B is true. Fundamental theorem of line integral tells us that. But we're trying to show A, B, and C are all equivalent to each other. So what we will prove is that B is equivalent to C. That's going to be theorem 3 below. And then we will also show that C implies A. That's going to be theorem 4 below. And with that chain of implications, we get that all three of these are equivalent. If any one of them is true, all of them are true. So again, we've already seen that A implies B. That's the fundamental theorem of line integrals. Now what is C? I haven't really said what C is. C is just saying that the integral around a closed path is 0 for any closed path in D. We use the little circle notation around our integral sign just to indicate that this is an integral around a closed path. It's not necessary to put it there, but it's just a reminder to us that, oh, this integral, it's going around a closed path. C is a closed path. So the integral around a closed path is 0. And so what we have is the equivalence of all these things. If f is conservative, then the integrals are path independent. An integral around a closed curve is 0. If any one of these is true, all of them have to be true. So let's go ahead and prove that B and C are equivalent. And that's basically what we're doing. Maybe I should back up. What we're doing in this lecture is we are proving this. We've already got part of it done. A implies B. That was the last video. But we are going to prove B is equivalent to C and C implies A. And so this gives us our properties of conservative vector fields. Conservative vector fields are precisely those vector fields for which, when you're interested in open simply connected domains, they are the vector fields where integrals are path independent, integrals over closed curves are 0. So those are our properties of conservative vector fields. So let's go ahead and prove that B and C are equivalent. We'll just make a note here that what we're doing here is we're proving, or this theorem 3 is that B and C are logically equivalent. One implies the other. This is what we want to prove. So we'll prove this direction first. You might say, well, where am I getting the direction from? In the statement of the theorem itself, there's an if and only if. So that's a conditional that's telling us that if it's independent of path, then the integral is 0 for every closed curve. But then the reverse implication is also true. So that's what if and only if means. And so we're just going to prove the first implication. So let's start with our assumption. We will suppose the integral is independent of path. Okay, so that's our assumption. Now we want to prove that the integral around any closed curve is 0. So we're going to let C be a closed path in D, and we want to show that the integral around it is 0. So let's also let x0 and x1 be 2 points on C, and we'll split C into 2 curves. So the idea is we've got this closed curve C, or closed path C, and we've just let x0 be some point on it and x1 be another point on it. And we've used that to split our curve C into these 2 curves, C1 and C2. Because we know by our assumption that the integral is independent of path, then we have that the integral along C1 of f dot dr is equal to the integral of C2 of f dot dr, since path independent. So that was our assumption, and there's where we used it. So now we'd like to show that the integral around all of C is 0. So now the integral around all of C, how can I get the integral around all of C? Well, I can first go around C1, or along C1, and then from that I will go along C2 but in the backwards direction. So I'm basically trying to go around this whole loop, and so once I've gone from x0 to x1 along C1, then I go from x1 back to x0 along C2. So that is, we're going along negative C2. And that's equivalent to then the integral along C1, f dot dr, minus the integral along C2 of f dot dr. But from star here, this equation star, we know that those two integrals are equal. So this is equal to 0 by star. And so that means for any closed path in D, that's what we started with. Our second sentence is, let C be any closed path in D. We've just got that the integral is equal to 0. And so that proves the implication that if the integrals are independent of path, then the integral is 0 along any closed path. We want to do the opposite implication. But for this, basically the argument is all the same. So similarly, just with maybe a few changes. So similarly, if the integral along C of f dot dr is equal to 0 for all closed paths C, then we get that the integral along any curve C of dr is path independent. And so how do we get that? I've written the word similarly here to indicate that it's pretty much the same work above, but here's the idea. We know that the integral is equal to 0 for any closed path. So we have this integral here is equal to 0. But that integral there is equal to 0 is just this integral equal to 0. And since that's equal to 0, it means that the integral along C1 is equal to the integral along C2. And so we get our path independence. So there's our proof of theorem 3. So now we are, in terms of the statement above, we have this proven, we have just proven this equivalence, and now we've got to prove that C implies A, and that's this next result, theorem 4. And this one ends up being the most challenging, if you will, of the bunch to prove. So we're going to have to be a little creative in how we prove this one. And the reason is because if we think about what it's asking us to show, it's asking us to show that if our line integral is independent of path, then our vector field has to have a potential function. And so there has to exist a function for which the gradient of it is capital F. And we're working purely abstractly here, so that means I'm going to have to construct what my potential function is. So in terms of what we're doing up above, we're now showing that C implies A. And so we'll start with letting our vector field be P xy I hat plus Q xy j hat. And we will let AB be some point in our domain D, and xy be any point in D. So the idea is we fixed a point AB, and then we've let xy represent any other point in D. And we're going to now define a function little f, which we're going to claim to be the potential function for our vector field. How are we going to define this function? Well, little f of xy is going to be defined to be the integral from AB to xy of f dot dr. And so this, when I've written it like this is telling you that I haven't actually told you what path I'm going from AB to xy. I'm just saying do the line integral from AB to xy along some curve and call that resulting value f of xy, because it's going to depend on the terminal point xy. Because I haven't told you what curve I'm integrating along, this could be ambiguous. But because of our assumption that the integral is path independent, this is well defined. There's no ambiguity. I can pick any path I want, do the integral, I'm going to get the same answer no matter what the path is. So this is well defined since path independent. So since that integral is path independent. Okay, so there we've got our function, little f defined. Now I just need to show you that this is the function whose gradient is big F. So I need to show that the partial derivative of this with respect to x is p and the partial derivative with respect to y is q. So now we show that del f del x is p and del f del y is q. In other words, so i.e. we are showing that the gradient of little f is big F. That's what we're going to show now. And here's how we're going to do it. So we've got this point x, or AB. That's our fixed point. And we've got our domain that we're working in. We've picked this other point, some arbitrary point xy. And because the region we are working over is open, I can find a disk around this that lives entirely inside the region D. So I can find a disk like that, and then I can find another point nearby. That other point nearby, it's going to be x1, y. And so basically there's a horizontal line segment that connects them. Just the x values are increasing. They have the same y value, the same height. And so what I've done is I've just created two curves here, a C1 curve and a C2 curve, to go from AB to XY. And this C2 curve is given by, if I want to do it as a parameterization, the C2 curve has to connect x1y to xy. So the y value is constant, but the x value is going to range from x1 out to x. So there's our curve C2. The idea is that this little f of xy is the integral from AB to xy of our vector field, and it's independent of path. So I've just created a path that is going to help me exploit some properties here and get the result I want. So I've created a path, and now we're going to work with it. So here we go. We're going to start with f of xy. That is going to be equal to, it's the integral along any path that connects AB to xy. So I will integrate first along the C1 path, f dot dr, and then I will integrate along the C2 path, f dot dr. And if I do that, the integral along the C1 path is from AB to x1y, f dot dr, and then the integral along the second path is from x1y to xy, f dot dr. Now what I want to show is that the partial derivative of f with respect to x is p. So let's go ahead and compute that. Del f del x. If I take the derivative of these two integrals, the first thing to note is that this first integral here, it does not depend on x. This is path independent, so it only depends on the initial point AB and the terminal point x1, y. and x1 is some fixed value. So it's independent of x. And so when I take its derivative, I get 0. And then the next one, I'm going to take its derivative with respect to x. Okay, so for that second one though, I can evaluate it, the integral, using this parametrization C2. So it's going to be the integral from x1 to x f dot dr. So what is our f? Our f is p comma q dot dr. What is dr in this case? Maybe I should write that down here. R prime of t is 1, 0. So that means when I work out this f dot dr, I get the p part surviving, and then I get a dt. And that's p at what? It's p at the parametrization of the curve, ty, and then we get a dt there. The q doesn't come up because of the fact that in our r prime of t, we've got a 0 for our second component. And so now I'm differentiating the integral of this function p of t, where the integral goes from x1 to x. So this is a fundamental theorem of calculus problem. It just says you want to differentiate an integral, you just pop that limit of integration in. And so this becomes then p of xy. And that's precisely what we wanted to show. Right? That's what we wanted to show. We wanted to show that df dx is p, and we've done that now. By a completely analogous argument, similarly, we will get that df dx is equal to q of xy. And so therefore, we've just shown that the gradient of this function f, which we constructed, is the vector field big F. So the bottom line is we were able to construct the potential function from the vector field, and we were able to do this because we used the path independence to our advantage, and we cooked up a path that made sure we were able to get the result we wanted. So that's it for this part of the video. I just wanted to focus on the theoretical properties. So let's back up to talk about the main properties we just had in this video, and that is this equivalence of these three statements. As long as we're talking about an open and simply connected region D, f is conservative, or it has a potential function. In other words, it's the gradient of some potential function. As long as the line integrals are path independent, or equivalently that the integral around any closed curve is 0. In the next video, we will look at how to figure out, given a vector field, how to figure out if it is conservative or not. And we will use the results here for these equivalences to detect whether a vector field is conservative. And once we know it's conservative, then we will look at how to construct its potential function for a given concrete example. So we'll see you in the next video.